In this section, we want to expand upon the topic of U substitution. Now, U substitution, I don't know if you ever really thought about it, but it's really only for a single variable. But what if you want to change more than one variable? That's what we're going to work on in this section. So let's first review U substitution. So you take your original function and you change your x out by defining x as some function of u, and then use the derivative of u du. So that equation, x equals g of u, can be described as a transformation equation, and it defines the change that we're making in the variable. Now, why did we do this in Calc 1 and Calc 2? Well, we did it because it made the integration simpler, sometimes possible, right? So sometimes we couldn't do it without a U substitution. All right, but now we want to make this happen for more than one variable at a time. So we want to do it for double integrals. So that means that we're going to have to transform not just our x, but also our y. So x is going to be some function of u, and y is going to be, some function of u and v. So we'll have two variables. Sorry, this is 2 dimensions. So 2 variables, and y will be some function of 2 new variables. So 2 dimensions, we need 2 new variables. This is called a transformation. T. All right, now when you make this transformation, you have to do a little bit of work. So up here, when we did it in 1 dimension, you can see that we had to do this g prime of u. And anybody who's ever been in Calc 1 knows that you have to do this work where you set up what your derivative is going to be in that new transformative equation, and then work from there. So we have to do that as well in 2 dimensions, but it's right here. It's called the Jacobian, right? Named after the person that thought of it, right? So it's called the Jacobian. It's the Jacobian of that transformation. And it's more complicated than just the derivative. So if you remember how we did it up here, we would say, oh, du over dx is equal to some derivative. And then we would say, okay, then du is equal to g prime of u dx. And then we would use the differentials and we would go from there. That's what we're going to do down here, but it's more complicated. It's right here. The Jacobian is that. Now, those vertical bars should look familiar to you. This is the determinant. We kind of did this when we were doing cross products back in the day. So what it is the cross product of the matrix. So determinant of the matrix is what it's called. So you take xu and then yv and then xv yu. And so you go across. You go xu times yv minus, and then xv times yu. It's very much like, it's a smaller component of what we were doing when we did the cross products back in chapter 11. Sorry, chapter 13 in the newest edition. So let's see an example where we can find the Jacobian. So we're going to find the Jacobian for changing a rectangular integral to a polar integral. So we're going to go from a rectangular to a polar. So that's a type of transformation, right? So if you're going to take from rectangular is x and y, and if it's going to be in polar, we know that's r cosine theta, r sine theta. So that's a transformation, right? This is h of r theta, this is, or excuse me, g of r theta, to keep my letters consistent, and this is h of r theta. So our new variables will be r and theta. And we've actually already done this before, but let me show it to you. So that Jacobian would be equal to x sub r, x sub theta, y sub r, y sub theta, right? Because r is my u and theta is my v. And so x sub r, the derivative of this with respect to r, would be cosine theta. the derivative of x with respect to theta would be negative r sine theta. The derivative of y with respect to r would be sine theta. And the derivative of y with respect to theta would be r cosine theta. So then when we crisscross, we take cosine theta times r cosine theta. So that's r cosine squared theta minus, and then negative r sine theta times sine theta. So negative r sine squared theta. So that's r squared, r cosine squared plus r sine squared. And that should be setting off little bells in our heads because that's r. Now, why are we not surprised by that? Well, because remember, when we switch from rectangular to polar, let me make a note real quick. We have to throw in this r here, remember? So when we go from dy dx, it becomes r dr d theta. And we proved that that was the case before, but now this backs it up, right? This is why that's happening, or if you will, this is another reason why that's happening. The Jacobian has this r in it, and therefore when we change and we transform our variables from x and y to r and theta, we have to have an r put in there for good measure. So that's a second proof that we have seen for why r is in there. Now let's look at how the regions in the planes are related to each other. And actually this is backwards. So this is going to be the r theta plane over here. Lowercase r, sorry. R theta plane over here. And this is going to be the xy plane over here. I'm going to go that direction. Okay, so let's look at a rectangle in the r theta plane. So we have a rectangle. This is the r axis. This is the theta axis. And there's our rectangle. Now, we want to consider all four of the sides and how each of the four sides would transform into the xy plane. Sorry, that is meant to be a rectangle. That's supposed to be straight up and down. Sorry about that. Okay. Well, there's four sides to this, so we have to consider how each of the four sides would translate. All right, so let's start with the bottom. So the bottom down here. All right, so let's look at the bottom. On this bottom line, theta equals 0 the whole time, and r is equal to, well, it transforms, right? So theta equals 0, and it starts here at 0, and it goes all the way to 2. So r, let me put a colon after that instead of an equal sign. R goes from 0 to 2. Okay, so how would that start? So at the start, we have r equals 0, theta equals 0. So r and theta, x is r cosine theta. So that'd be 0 cosine of 0, which is 0. That's a 0 there. And then y is 0 sine of 0, which is 0. So we're going to start at 0, 0 in the xy plane. And we're going to end at, okay, 0 and 2. So 2, r equals 2, theta equals 0. Okay, so x would be 2 cosine of 0, which is 2, and y would be 2 sine of 0. The sine of 0 is 0, so this is 0. Okay, so I'm going to draw a companion picture. I'm low on space, so I'm going to kind of sneak it in over here. Okay, so here's my xy axis. X-axis, y-axis. Okay, so we just made it so that the bottom in the r theta plane translates to 0, 0 going to 2, 0 here. So that's the new bottom for our new rectangle that we're going to draw. Okay, now let's look at the right-hand edge. So on this right-hand edge right here, let me do it in a highlighter here. There's the right-hand edge. Okay, so the right-hand edge starts at down here, right? So r is equal to 2, and r is equal to 2 the whole time. So r is equal to 2, but theta goes from 0 to wherever this is. Let's just say for fun it's pi over 3. So let me pretend. This is pi over 3, and this is 2. So I'm just establishing, right? It could have been anything. I just picked 2 and pi over 3. So 0 to pi over 3. I mean, you could have picked 4 and pi over 7 for all it matters, right? So, okay, so now let's translate over here. At the start, right, r equals 2, theta equals 0, all right? Well, okay, that's going to mean x equals 2 cosine of 0, which is 2, y equals 2 sine of 0, which is 0. So I'm going to start at 2, 0, which is right here. But I'm going to end at r equals 2, theta equals pi over 3. Okay, so that's x equals 2 cosine pi over 3, and y equals 2 sine of pi over 3. So that's 2 times a half, which is 1. And this is 2 times the square root of 3 over 2, which is the square root of 3, which is about like 1.7 or so. So that means that I'm arching backwards to 1 and about 1.3. So it's going to go like that and end up there. All right, so now let's look at the top up here. So we got the top up at the top of this. Up here, right, r is going to change. Theta is pi over 3 the whole time. But r is going to go from 2, where it starts, back to 0. Right? Because we're working our way, if you will, around this rectangle. So we're going from 2 to 0. Okay, so let's think about the start here. So at the start, r equals 2, theta equals pi over 3. Okay, so that means that x equals 2 cosine of pi over 3, which we already know, that's 1, we just found that. And y equals 2 sine of pi over 3, again, which we already know, we just found that. So we're going to start at the same spot we just ended in, which is great. Now, where are we going to end? Right? At r equals 0, theta equals pi over 3, which means we're going to end at 0, 0, right? X equals 0 cosine of pi over 3, which is 0. Y equals 0 sine of pi over 3, which is 0. So we're going to go straight back to that. Well, what about that left-hand side? Where did that go? Right, so over here, we had a left-hand side. Okay, so the left-hand side was theta, well, r equals 0 the whole time, and theta goes from pi over 3 back to 0. So at the start, we have r equals 0, theta equals pi over 3, which once r equals 0, we know x is 0 and y is 0, right? 0 times anything is 0. And then the end would be still r equals 0 and theta equals 0. But again, that means x equals 0, y equals 0. So that whole side collapses to a point right here at the origin. So every single piece of this rectangle in the polar coordinate system translated over to some new object in the xy coordinate plane. The bottom pink here became that piece. The side, right side over here, became that piece over here. the top here became that section over here, and then the green became a point. Now this is a rectangle. That is a sector of a circle. So that's where the term polar rectangle that we've seen before comes from. Right? A polar rectangle is a rectangle in the xy plane, excuse me, rectangle in the r theta plane. In the r theta plane transforms to a sector of a circle in the xy plane. Oh, the dash is in the wrong spot there. It should be xy dash.